We're going to be using the definition of the integral to prove that the integral from a to b of x dx is the same as b squared minus a squared over 2. And this is going to take a lot of algebra, and it's going to be a little bit of fun because of that. All right, let's start off. We're going to have our integral from a to b x dx. We know by definition of the integral that this is equal to the limit as n goes to infinity, and we always want to go back to our definition when we're doing this. Sum from I to n, f of x I star, change of x. And that xi star just means that you could do the right, the left, or the center of the rectangle that you're using to chop up your area. So we have a couple pieces here. I'm going to start off with our change of x. Change of x is always going to be the endpoints subtracted and divided by how much you're chopping things up into, how many pieces we're chopping our rectangles up into. And in this case, it's n. So our change of x is b minus a over n. Second part is, what is this f of xi star? I'm going to drop the star, the asterisk up there, but I'm going to just keep on using the rest. So our xi is going to be a plus I change of x. And we can rewrite that because we know our change of x is b minus a over n. So we can pop that in there. And that should be a plus there. There we go, which means that f of xi, since our function is just x itself, is just going to be a plus I b minus a over n, because this is our function f that we're working with in this case. All right, so this tells us that we are looking at the limit as n goes to infinity of the summation I is equal to 1 to n, and we're going to pop in our a plus I b minus a over n, and then instead of change of x, we're going to pop in a b minus a over n on the outside. All right, so that is the basic setup of what we're looking at. The next thing that we're going to do is a bunch of algebra. We're going to start by taking this element right here and bringing it all the way out, because you'll notice there's no I values in it, which means that it's not going to be affected by the summation. So we can pop that all the way on the outside. So we're going to have our limit as n goes to infinity of b minus a over n. And then we have our summation I is equal to 1 to n, a plus I b minus a over n. All right, next thing that we can do, and I'll put parentheses here again, is we can actually distribute our summation. Summations are going to distribute over sums, which is not surprising. So we still have this b minus a over n. And then I'm going to put a big square bracket here. We have our summation I is equal to 1 to n of a, which notice we don't have any i's in there at all. And I will say something about that in just a second here once I get the rest of this out. B minus a over n. All right, so there's a couple things we're going to do. First, again, we notice we have a b minus a over n that we can pull out in front of the interval there. Second of all, this, another way of writing it, is that we are just adding up a n times. So the letter a is there n times, which means this is the same as a times n, because you have n copies of that. So let's do our rewrites. So this gives us our limit as n goes to infinity. We have our b minus a over n. And then we've got our big brackets, an plus, we brought our b minus a over n out front. I is equal to 1 to n of I. All right, and now this bit right here, that's what we were wanting to get rid of, because if we can get rid of that sum, at least there's only a limit, no sums left. All right, we know that if we wrote this out, it'd be 1 plus 2 plus 3 all the way up to plus n. And if you do a little bit of math here, you'll notice that this is n times n plus 1 all over 2. And the idea behind that is that we are taking 1 plus n is n, 2 plus n minus 1 is also n plus 1, and we kind of pair up all the way through this, our numbers. We have n plus 1 is what they are all equal to. We have n times that we go through this, but it's actually n over 2 because you're counting everything twice. So there's your summation right there. Rewriting everything, we end up with the limit as n goes to infinity of b minus a over n, and then we have ab plus b minus a over n times n plus 1 all over 2. There we go. And we'll notice we can cancel out our n's then, which makes this a little bit nicer. So now we have the limit as n goes to infinity of b minus a over n, a times n plus, and I'm going to squeeze everything up into one bit on the top there on the numerator. We're just going to push that over to the numerator. And now we're going to take our b minus a and we're going to distribute that so that we can get rid of our parentheses there, because we want to make this a little bit slimmer as we go through this. So we have b minus a over n times a n plus b minus a, and I'm going to write squared because we have 2 copies of that now, over 2n. And as you may notice, our n's are going to cancel in the first bit again. So now this looks much better. We get the limit as n goes to infinity of b minus a times a. You'll notice there are no n's in that first term now. So we got rid of all of our n's, and all we have is the n's on our second term. And I'm going to actually pull those apart a little bit. We have n plus 1 and n. And notice what's going to happen as n goes to infinity. This is going to go to 0. And how do we know that? As a side note, if we pull out, if you're looking at n plus 1 over n, you can rewrite that as n times 1 on the denominator and n times 1 plus 1 over n on our numerator. Our n's would cancel out, and this is 1 plus 1 over n over 1. And the 1 over n as n goes to infinity goes to 0, which means your entire bit ends up being 1 over 1. So all of that should disappear. And I wrote 0 here. I meant 1. There we go. So we end up with the limit. Actually, our limit is taken at this point. So we have b minus a times a plus b minus a quantity squared over 2. So now we don't have any n's at all. We've gotten rid of our limit. The only thing left to do is to smush these two together and get our b squared minus a squared is equal to 2. So let's get a common denominator first. And we're going to do that by multiplying both on top and bottom of our first term by 2. Next up, we also want to, let's distribute this. Let's actually, I'm going to rewrite this a little bit, and then we'll distribute everything. And we get b squared minus 2ab minus a squared, or plus a squared, all over 2. So we want to factor that out and then distribute everything. 2ab minus 2a squared. And let's all push this together onto one numerator since we have a common denominator. This is going to give us a nice information here because our 2ab's cancel out. And notice one of our a squareds cancel out. And we are left with b squared minus a squared all over 2 as our solution, which is what we were looking for. Thank you for listening.